Welcome, fellow chemists, to the fourth and final mass spectrometry video in this series. 3 videos ago, we learned how to read a spectrum, and today we will focus on what to expect to see in a spectra of amides, acids, esters, and aromatic compounds. Consider each of these 4 a kind of quick hit, as some of the particulars may have been mentioned in a previous video by this point. The last spectra is a practice courtesy of Reddit. In this video, I've simplified the animations to make things easier, meaning I've cut out all electron pairs and most instances of resonance. I will include the charge as it is the cations which are detected. Amides, in particular the primary version, have 2 fragmentations you should be aware of. The first is simple, and it is when the bond between the carbonyl and carbon next to it breaks. This produces primary alkyl radicals which go undetected. The cation, which does get detected, is more stable as the charge is shared between the oxygen and carbon atoms. Although the original amides increase in size going down the screen, these fragments are all identical and have mass 44. The second type is the McLafferty rearrangement, which only occurs if the alkyl chain is long enough. The first amide is too short, so it will not undergo this process. Meanwhile, the other 2 amides contain a gamma carbon, and thus gamma hydrogen, so it will occur on both. When it does, they produce alkenes which go undetected. As for the cations, the charge is once again shared between oxygen and carbon, and they have mass 59. So to show these on a spectrum, primary amides will produce a fragment of mass 44, and if McLafferty rearrangement occurs, one with mass 59. The heights of the peaks would depend on the molecule that produced the spectrum. And as a bonus, remember that statement about amines having odd molecular ion values? Well, the same is true for the amides. It is quite nice of nitrogen to be such a big help. Now on to the carboxylic acids, where I'm going to simplify the animations even more. From here, I will just highlight the fragments you should expect to see. I suggest trying with paper and pencil to determine the mechanism for each fragmentation and if charge is shared among atoms in the fragment. If you're feeling a bit of deja vu, it's not a glitch in the matrix. All I did was switch out the amine groups from the previous molecules for the alcohol. Given the structural similarity, you would not be shocked to hear that McLafferty rearrangements occur here too. Like before, the top molecule does not have a long enough alkyl chain, but the bottom 2 do. Since the mechanism is the same in both, the fragments produced are identical. So if the acid structure allows for it, expect a peak for this fragment, but unlike the amides, it has mass 60. There are, however, 2 other fragmentations you should expect, and both are pretty straightforward. First is the loss of the alcohol group. Since the alcohol has mass 17, the detected fragments all have masses of 17 less than the M value. The second is from the loss in the entire carboxyl group, which has a mass of 45. In this case, the cations all have masses 45 less than the M value. This spectrum will show those 3 fragments for pentanoic acid, which has an M value of 102. The fragment formed by McLafferty rearrangement is at 60. There is a peak at 85, or M-17, which represents the fragment detected after losing the alcohol. The peak at 57, or M-45, is the alkyl cation after the loss of the carboxyl group. These peaks are taken from the actual spectrum of pentanoic acid. Just because the peaks are expected at a particular value does not mean they are obvious. On to esters now, which kind of have the acid structure, except instead of hydrogen there is some alkyl group. There are 2 simple fragmentations to look out for with the esters. If the bond to the alkoxy group breaks, the fragment with the carbonyl gets detected. In these examples, they increase with mass from the top down, starting at 57, then 71, and finally 85. The other expected fragmentation occurs when the bond between the alkyl group and oxygen breaks. It results in a carboxylate, which we can ignore, and the alkyl cation, which gets detected. Coincidentally, the first molecule produces another fragment of mass 57, the other 2 are 43 and 29 respectively. Now to demonstrate where these fragments show up for the middle molecule, we see the alkyl fragment at mass 43, and carbonyl one at mass 71. I left out other peaks from the real spectrum, but both of these are as prominent as depicted here. The database, which you can find in the script, showed no molecular ion at 130, and the peak data had no value either. For the other esters, the molecular ion was either very tiny or non-existent. For our last stop, simple aromatic compounds are molecules containing a benzene ring. Aromatic structures are fairly stable, and these rather simple ones like phenol to start often have clear molecular ion peaks. When provided the intensities for the M and M+1 peaks, the number of carbons can be calculated, and it results in 6 as expected. The peaks at 65 and 66 are largest after the base, and potential identities for these cations are C5H5 and C5H6 respectively. When I switch to aniline, which contains an amine group, the molecular ion peak falls on an odd number. We can use the M and M+1 intensities to confirm the number of Wait a minute, this isn't even close. Did you read the note in the script on video 2? Because now you are seeing it in action. This spectrum also contains peaks at 65 and 66, which are best explained with the fragments from before. Even something as complex as acetaminophen shows a strong M peak. It's not the base peak, which is sensible as larger molecules have more locations for fragmentation to occur. The calculation of the number of carbons for this molecule results in 8, but only just. You should try and reason out the potential structures for the fragments resulting in peaks at 109 and 43. You'll find the answer in the script. At this point, you may be reaching for some acetaminophen, but let me show you how we can apply what we have learned over the past 3.5 videos. It is about time I show a full spectrum, and the inspiration for this example comes from a Reddit post that came up while I was working on this series. There are a lot of peaks, 60 in fact, and some of them look like random noise. Many spectra look like this, which is why I decided to modify the ones I've included until now. Without context, as in knowing there might be a halide or other functional group, you may think this is impossible, but it's not. Pause the video and give it a go yourself. The spectra does not contain a clearly obvious molecular ion peak. The last peak, if we can call it that, was at 129 and the x-axis ends at 130. We can infer the instrument did not record anything higher than that, so it's not much, but it's a start. Now the base peak at 45 is easy to identify. In this and previous videos, we have looked at fragmentation patterns. This means if two different molecules produce a fragment of the same mass, it may mean there is a structural similarity between the two. We saw in the previous video that an alcohol on position 2 would produce a fragment of mass 45. On this model, that would happen if the bond to the larger alkyl group broke. However, remember, it is possible to break the bond to the first carbon of the parent chain too. If it did, we would have a peak at M-15 because we lose a methyl. There are two peaks that fit this potential fragment. But we can narrow this down further because alcohols have a special fragmentation where they lose a water molecule. The alcohol leaves as does the gamma hydrogen from the alkyl chain. This would result in the peak at M-18. These two peaks are separated by exactly 3, which makes a good candidate for these fragments. Because we are subtracting from M, the peak on the right is M-15 and the other is M-18. With a bit of math, we can solve for M and we get 130. The alcohol is on position 2, and a bit of figuring out regarding the M value leads to the identity of the molecule as octan2-ol. It was a nice coincidence to find this problem posted to Reddit as I was working on this series. Hopefully I was able to use that problem to demonstrate that you do not need some absurd professional level of knowledge, but instead a basic understanding and a bit of logic to tackle the analysis of a spectrum. While I am done with mass spectrometry, this instrumental analysis series will continue with infrared spectroscopy. Development of those videos is in progress, but the third and final stop in this series, NMR spectroscopy, awaits us in the distant future. Until the next video is up, thank you very much for watching. Please feel free to leave any questions or requests in the comments below.